Hey everyone, and welcome back. Today we're going to do a deep dive into the world of heat transfer.
Oh, yeah.
It's something that's all around us all the time, but we don't really always think about it.
Yeah, we kind of take it for granted, don't we?
We do. So before we get into the really fascinating research that we have here,
Okay.
let's just make sure we're all on the same page about what exactly heat transfer is.
Yeah.
So we're talking about the movement of heat energy, and it's always going from a hot object or area
Right.
to a cooler one, right?
It's all about equilibrium. Nature's always trying to kind of balance everything out.
Oh, I like that.
Yeah.
Finding that balance. Okay.
Yep.
So we know that it's always on the move, but how does it actually get around? How does it move?
Well,
Our sources talk about three main methods:
okay.
conduction, convection, and radiation.
Yeah, those are the big three.
So are we ready to dive into those?
Absolutely. Let's get into it.
All right, let's start with conduction. And I think a really good example of this is if you imagine yourself holding a hot cup of coffee or tea, why does your hand get warm?
Mm-hmm.
So that's conduction in action, right? It's all about that direct contact.
Direct
The
contact.
heat energy is literally moving from molecule to molecule from that hot mug
Right.
to your cooler hand.
Exactly. And the rate that it transfers at can be affected by a bunch of factors.
Oh, really?
Yeah, so the material the mug is made of makes a huge difference.
Okay.
So a metal mug is going to transfer heat way faster than a ceramic one.
Oh, that's why my metal water bottle gets so cold when I put ice in it.
Exactly.
Yeah.
That's conduction at work.
That's so cool.
And it's not just the type of material. It's how thick the mug is and the area that's actually touching your hand.
So a really thick mug is going to take longer to transfer that heat.
Exactly. It's like adding extra insulation,
Okay.
which slows down that heat transfer.
That's interesting. Our sources had this example about a copper rod, and they calculated that if you heat one end of this rod up to 100 degrees Celsius,
Okay.
and the other end is at room temperature, 20 degrees,
Mm-hmm.
the heat's going to flow through it at a rate of 640 watts.
Wow, that's a lot. Like a small space heater.
Yeah. So you can really imagine how much energy is moving through that rod.
Yeah, it's impressive.
So conduction is used in a lot of everyday applications,
Well,
right?
Yeah, definitely those heat sinks that are in computers and stuff.
Yeah, they pull heat away from those sensitive little components.
Exactly. It's using those principles of conduction to keep things cool.
That's super interesting. Okay, so we talked about conduction,
Mm-hmm.
which is direct contact. What about convection?
So convection's a little different.
Okay.
It's all about the movement of fluids.
Fluids.
Yeah, like liquids or gases.
Okay.
So think about a pot of water boiling on the stove.
Okay.
You see those currents in the water?
Yeah.
That's convection.
So it's moving the heat all around?
Exactly. And there are two main types. Natural and forced.
Oh, okay. What's the difference?
Natural convection happens on its own. You don't need any extra help.
Okay.
It's all about density.
Okay.
So warm air rises because it's less dense.
Makes sense.
Forced convection is when you use something to move the fluid around.
Like a fan.
Exactly. Like the fan in your computer.
Oh, okay.
It's forcing air over the hot components to keep them cool.
So it's we're helping that heat move along.
Yep. We're giving it a boost.
So is there a law that governs how all this works?
There is. It's called Newton's law of cooling.
What does that say?
It basically describes how fast something will cool down.
Okay.
And it takes into account things like the fluid's properties, how fast it's moving,
Mm-hmm.
and even the shape of the object.
So there's a lot that goes into it.
Yeah, it can get pretty complex.
That's fascinating. It's incredible how much science goes into something as simple as
I know, right?
boiling water.
It's amazing what you find when you start looking closer.
Okay, so we've covered conduction and convection, but our sources talk about one more method,
Yeah.
radiation. And this one sounds kind of mind-blowing.
It is. It's how heat travels through electromagnetic waves.
Electromagnetic waves, so light.
Kind of, but these waves are specifically carrying heat energy.
Okay.
And the crazy thing is, it doesn't need any matter to travel through.
So it can travel through space.
Exactly. Like the heat we get from the sun,
Wow.
that's radiation.
That is mind-blowing.
It is. It's like invisible heat rays.
Okay, so is there a law that governs how radiation works?
There is. It's called the Stefan-Boltzmann law.
Okay, tell me about it.
It basically says that the amount of heat something radiates depends on its temperature and a property called emissivity.
Emissivity, what's that?
It's a measure of how well something emits thermal radiation.
Okay.
So a perfect black body has an emissivity of 1,
Mm-hmm.
which means it absorbs all the radiation that hits it and emits the maximum amount of heat.
So a dark object is going to absorb more heat than a light one?
Exactly. That's why you wear light clothes in the summer,
That makes sense.
to reflect more of that sun's radiation.
Even though we can't see it, radiation is constantly at work around us.
Oh yeah, all the time.
Mm.
It's shaping how things heat up and cool down.
That's so cool. Okay, so we've learned about conduction, convection, and radiation.
The three main ways heat gets around.
Wow. They all seem so different.
They are, but they're all connected.
And they all play a role in like our everyday lives.
Absolutely.
But I'm guessing it's not always so clear-cut. Like in the real world, these things are all happening at the same time.
You got it. It's usually a combination of all three.
So like a hot cup of coffee is losing heat through conduction, convection, and radiation all at once.
Exactly. And that's where things can get really complicated for scientists and engineers.
How so?
Because when you're trying to design something, you need to take all three methods into account.
Yeah.
And it can be really tricky to predict how heat is going to behave.
So like when they're designing like a car engine, they need to make sure it doesn't overheat.
Right. And they need to consider all the different ways heat is being transferred.
Wow. That sounds like a really tough job.
It is. But it's also really fascinating.
It makes you realize like how much thought goes into designing even the simplest things.
Yeah, everything around us has been carefully designed with heat transfer in mind.
It's incredible. This has been such a great deep dive so far.
It has. We've learned so much about the ways heat moves around.
And we've only just scratched the surface. There's still so much more to explore.
I know, right?
So why don't we take a quick break?
Okay.
And when we come back, we'll dive even deeper into the fascinating world of heat transfer and its impact on our lives.
Sounds good. I'm ready for more.
All right, we'll be right back. So we've been talking about all these ways heat moves around conduction, convection, radiation.
Yeah, it's pretty amazing how it all works.
It is. But it makes me wonder, like, can we ever actually stop heat transfer?
That's a good question.
Like, could we create, like, the ultimate insulator?
The holy grail of thermal engineering.
Yeah. Something that prevents any heat from escaping.
Well, it's definitely something that scientists and engineers are constantly striving for.
Okay.
But achieving absolute zero heat transfer, that's a tall order.
So even with all our technology, we can't completely stop it.
It's tricky because remember, heat always wants to move from hot to cold.
Right. Nature wants to find that balance.
Exactly. It's like a fundamental law of the universe.
So even with like the thickest insulation, some heat's always going to sneak through.
Pretty much, yeah. Even the tiniest temperature difference is going to create that drive for heat to flow.
Okay, so like it's kind of like trying to keep a gas in a container.
Yeah. Those gas molecules are always bouncing around, looking for a way to escape.
So no matter what we do, heat's always going to find a way.
It's persistent.
Yeah.
But we can definitely try to slow it down.
Right. And that's where insulation comes in.
Exactly. Insulation is all about creating barriers that resist heat flow.
And like, how does that actually work?
Well, there are a bunch of different ways, but a lot of it comes down to trapping air.
Air. Like the stuff we breathe.
Yep. Air is actually a really good insulator.
Huh. I never thought of it like that.
It's better than a lot of solid materials like wood or even concrete.
Interesting.
So a lot of insulation works by creating little pockets of air.
Oh, okay. So like those fluffy pink fiberglass bats that they put in walls?
Exactly. They're basically just a bunch of air pockets.
So it's like creating a maze for the heat.
Yeah. It has to work a lot harder to get through all those tiny air pockets.
That makes sense, and that's why it's so effective at like keeping our houses warm.
Right. And we see this principle used in all sorts of things.
Like what?
Well, like a down jacket.
Oh, yeah.
Those feathers trap air, which creates a layer of insulation around your body.
That's so cool. And what about those double-paned windows?
Same idea. That gap between the panes of glass is filled with air or sometimes a special gas,
Right.
which helps to reduce heat transfer.
So we're basically using air to like trick heat into slowing down?
You could say that. It's all
Yeah.
about manipulating those natural processes.
Yeah. I love it. It's amazing how something so simple can be so effective.
Yeah, it's a testament to human ingenuity.
Okay, so we've talked about how insulation works in our homes, but I bet this stuff is important in other fields too, right?
Oh, absolutely. Heat transfer is a huge factor in tons of different industries.
Like what?
We'll take architecture, for example.
Okay.
Architects need to understand heat transfer to design buildings that are energy efficient.
Right, so they can stay warm in the winter and cool in the summer.
Exactly. And they have to consider things like the materials they use, the orientation of the building, and the climate.
So there's a lot of planning that goes into it.
Oh yeah, it's a complex process, but it's crucial for creating sustainable buildings.
And what about like aerospace engineering?
That's another great example. Spacecraft design is all about managing extreme temperatures.
Yeah, I can imagine.
On one side, you've got the intense heat of the sun,
Right.
and on the other side, you've got the frigid cold of space.
That's crazy.
So engineers have to use all sorts of techniques to control heat transfer.
Like,
Well, they use reflective surfaces to minimize heat absorption from the sun,
okay.
and they use insulation to prevent heat loss from the spacecraft.
Makes sense.
And they also use these things called heat exchangers to distribute heat evenly.
Wow, so they're really using everything they've got.
Yeah, it's a huge challenge, but it's essential for keeping the astronauts safe and the equipment functioning properly.
It's amazing how this stuff is so crucial in like these really advanced technologies.
It really highlights how fundamental heat transfer is to everything we do.
Okay, so we've talked about insulation and architecture and aerospace engineering. Is there anything else that heat transfer plays a role in?
Oh, tons of things. Like even the formation of stars.
Wait, really?
Yeah. In those giant clouds of gas and dust where stars are born, gravity pulls all these particles together.
Okay.
And as they collide, they generate heat.
So it's like a snowball effect,
Exactly. And eventually that heat gets so intense that it triggers nuclear fusion.
which is what makes a star a star.
Yep. It's the process that powers the sun.
That is mind-blowing. So heat transfer is not only essential for life on Earth, it's also responsible for the creation of stars.
It's a pretty big deal. It's one of the most fundamental processes in the universe.
This is incredible.
I know, right?
It's like we've been taking heat transfer for granted all this time.
It's easy to do. But once you start learning about it,
Yeah.
you realize just how important it is.
This deep dive has been amazing.
It has. It's really opened my eyes to the world of heat transfer.
So what are some of the ways that we've used our understanding of heat transfer for like technological advancements?
Oh, wow. There are so many examples.
Like what?
Well, I mean, think about the steam engine.
Oh, yeah.
That was a huge breakthrough. That was all about harnessing the power of heat.
And it really revolutionized like transportation and industry.
It did. And then more recently, we've got all sorts of amazing technologies that rely on heat transfer.
Like what?
Well, things like power plants.
Okay.
They use heat to generate electricity.
Right.
And then you've got all sorts of things in electronics.
Yeah, like those heat sinks we were talking about earlier.
Exactly. They're essential for keeping our computers and phones from overheating.
It's amazing how we've been able to like manipulate heat transfer to create all this technology.
Yeah, it's
Wow.
really impressive.
Yeah.
And as we continue to push the boundaries of technology,
Mhm.
our understanding of heat transfer is only going to become more important.
What about like renewable energy?
Oh, yeah, that's a huge area where heat transfer is playing a critical role.
Like how?
Well, things like solar panels.
Okay.
They convert sunlight into electricity,
Right?
and that process involves a lot of heat transfer.
So we're using heat from the sun to power our homes,
We are. And then there's geothermal energy.
which is.
It's basically using the heat from the Earth's interior to generate power.
Wow.
So yeah, heat transfer is really at the heart of a lot of these renewable energy technologies.
It's like we're learning to speak the language of energy.
Yeah.
Yeah.
And that's going to be essential for creating a more sustainable future.
I love it. This deep dive has been truly eye-opening.
It has. It's really made me appreciate the world around us in a whole new way.
It's like we're suddenly seeing all these invisible forces at play.
Yeah, we've got thermal vision.
I know, right? It's so cool. And it makes you realize like how interconnected everything is.
It does. From the tiniest atoms to the largest stars, heat transfer is this fundamental force that shapes the universe.
This has been such a great conversation. I feel like I've learned so much.
Me too.
It's amazing how something so seemingly simple can be so complex and fascinating.
Yeah, it just goes to show that there's always more to learn.
And that's what the deep dive is all about, right?
Mm.
Exploring those fascinating mysteries that are all around us.
Exactly. And sparking that curiosity and that passion for lifelong learning.
Okay, so before we wrap up this deep dive,
Mm-hmm.
I want to leave our listeners with a final thought to ponder.
Okay.
Now that we've explored the world of heat transfer,
Mm-hmm.
how do you think we can use this knowledge to create a more sustainable and energy-efficient future?
Ooh, that's a good one. It's definitely a challenge. But I think it starts with education.
Yeah.
The more people understand about heat transfer,
Mm-hmm.
the better equipped we'll be to develop those innovative solutions.
Right, and to make informed decisions about how we use energy.
Exactly.
No.
And it also requires collaboration between scientists, engineers, policymakers, and really everyone
Yeah, we all need to work together.
to create a future where we're using energy more efficiently and sustainably.
This has been an incredible journey. It's amazing how this seemingly simple concept of heat moving from hot to cold has such profound implications for our lives.
I know, right? It's everywhere.
And it's shaping the world around us in ways that we don't even
It
realize.
really makes you appreciate the power of science and the beauty of the natural world.
It does. And it makes you realize how much more there is to discover.
Absolutely.
Wow. It's incredible to think something as basic as heat moving around can have such a huge impact, like on everything.
Yeah, it really is. It's kind of mind-blowing when you stop and think about it.
It is. Like all this stuff we've been talking about, those invisible heat rays traveling through space, those heat sinks in our computers.
Yeah, like we've been taking it for granted.
Yeah, like we've gained a whole new perspective.
Totally. And like a new appreciation for how the universe works, all the little detail.
I know. It's like I'm suddenly way more aware of the heat, like everywhere.
It's like you've got a sixth sense now, a heat sense.
I love that. Like I can see those flows of energy.
Exactly. And the cool thing is there's always more to learn about it. Like we're just scratching the surface.
And all that new knowledge is going to lead to even more amazing technology.
Oh, definitely. The possibilities are endless.
This whole conversation has really made me think about how important it is to keep investing in research, like in this field.
For sure. Especially if we want to create a more sustainable future.
Exactly. Like if we want to move away from fossil fuels and all that.
Yeah, we need to get really good at managing heat.
So things like better solar panels, more efficient buildings.
Oh, and don't forget about harnessing waste heat.
Oh, yeah. Like all that heat that just gets released into the environment. We could use that.
Exactly. It's like a whole untapped energy source.
It's like we could solve a problem and create energy at the same time.
It's a win-win. And there are probably tons of other solutions out there, things we haven't even thought of yet.
This deep dive has been so eye-opening. It's amazing how this simple idea of heat moving from hot to cold can be so complex.
I know, and so crucial to everything around us.
It really makes you appreciate the power of science.
It does, and the beauty of how everything's connected.
It's been such a great conversation. I feel like I've learned so much.
Me too. It's been a blast.
So on that note, I want to leave our listeners with one final thought to chew on.
Okay, shoot.
Now that we've all explored the world of heat transfer, what do you think? How can we use this knowledge to create a better future?
That's a big question, but a good one. I think it's going to take a lot of creativity, collaboration, working together.
Right, like scientists, engineers, policymakers, everyone.
Exactly. We all need to be on the same page.
To make a real difference.
Yeah, to create a world where we're using energy more wisely, more sustainably.
Well said. So that wraps up our deep dive into the world of heat transfer.
It's been a wild ride.
It has. And until next time, keep those brains buzzing and never stop exploring.
And remember, there's always something new to discover. You just got to look for it.